Physics 2211 Lab 3 Black Hole Presentation. The purpose of Lab 3. Lab 3 was split into two parts. For the first part of the lab, we had to find the mass of the black hole. For the second part of the lab, using the mass of the black hole, we had to determine the initial velocity of a spaceship so that when it launches, it would not crash into the black hole. Part 1 Intro. The resulting black hole mass that I found using my Part 1 computational coding was 2.12962 times 10 to 34. And my system in this case was the star and the surrounding was the black hole. Formula used force of gravity, which is negative g times big M times little m over r squared. And g in this case is 6.67 times 10 to the negative 11. Big M equals mass of star, little m equals mass of black hole. And throughout the entire course of this lab, several Newton's second law formula was also being used. For example, the velocity formula, where Vf equals Vi plus F net divided by m times delta t. The position formula, where is Rf equals Ri plus V average times delta t. And F net equals F net parallel plus F net perpendicular. Parallel equals motion and speed of object. Perpendicular is changing direction of an object. And here is my Part 1 computational coding. You can see where before beginning into a deep dive to the other part of the coding, you can see that G is listed here and mass of the star, and delta T is 24 times by 3,600 because it's 24 hours times 60 minutes and times 60 seconds because the time interval needs to be in units of seconds. And I found dp dt parallel by using Newton's second law formula, the velocity and position. And then after finding dp dt parallel, I was able to find dp dt perpendicular because the formula is F net equals dp dt perpendicular plus dp dp parallel. And Part 2 Intro. The system is the spaceship. The surrounding this time, other than black hole, there's also the planet. And the initial velocity that I found through trial and error is negative 9.99 times 10 to the 7. And in the x direction and in the y direction is 7 times 10 to the 6. And here is the computational coding for Part 2. You can see before going into the formulas, there's the some of the initial values for the mass of ship, mass of planet, and then the black hole mass that I obtained from Part 1 coding. And I found F graph on planet by black hole and F graph on planet by ship, and then adding those two components together give me the net force on planet. And then I jumped into finding F graph on ship by black hole and then F graph on ship by planet. And then adding those two components gives me net force on ship. And then I move on to using Newton's second law formula, which is the velocity and position formula, to update planet velocity, planet position, ship velocity, and ship position. And what does this mean? Question. So essentially, they are different because they're calculated differently using different components. And when you calculate for the net force, there is a requirement of mass. But when you calculate for changes in momentum, there's not necessarily, you don't really need the mass. You can calculate it using position, velocity, and time. What if question? So essentially, I couldn't find a specific velocity for it to work, but logically, I feel like you would either have to lower the vector by a lot or increase it by a lot. I tried both, but still couldn't find the exact specific values that would have made my ship orbit the black hole. Possible errors. My initial velocity were not very specific, so I ended up having to do trial and error because my calculation was not entirely correct. So that might have messed it up a little bit, but it still ended up working. Thank you.